From the Library of Congress in Washington, D.C.
I'm Jennifer Harpster, a digital reference specialist with the Library of Congress Science, Technology, and Business Division. I'd like to welcome you to today's program, the Hubble Space Telescope, A New Beginning. This program is a part of a series of programs in 2009 presented through a partnership between my division and the Goddard Space Flight Center. One picture is worth 1,000 words. I can't think of a more appropriate statement to describe the Hubble Space Telescope Program. For over 20 years, the Hubble has given us pictures of our universe, the birth and death of stars, the moons of Jupiter, the rings of Saturn, asteroids over 300 miles long. These images have revolutionized our understanding of the universe. Our speaker, I skipped a sentence, sorry. This year, NASA sent the final servicing mission to Hubble, which has left the telescope at the apex of its capabilities, far more powerful than it ever has been before. Our speaker today is Dr. David Leckrone, a senior project scientist for the Hubble Space Telescope Program, who has recently retired. Dr. Leckrone received a bachelor's degree in physics from Purdue University and a master's and Ph.D. in astronomy from UCLA. He has worked at Goddard since 1969 and on Hubble since 1976. He is an internationally recognized authority on the chemical elements of stars. Earlier this year, he was awarded the NASA Distinguished Service Medal, which is the highest award the agency bestows. Today, Dr. Leckrone will share with us accounts of the final service mission to Hubble and what the future holds for the world's most famous space telescope. So please join me in welcoming Dr. David Leckrone.
Thank you, Jennifer. Good afternoon. I have a habit of moving around, and so but this is the microphone, so I will try to stay glued, but if you can't hear me or if we get interrupted because of that little problem, tell me, please. This can be interactive. Okay. I do want to give you a little commercial. Tonight at 8 p.m. on PBS, so public television, probably WETA here in Washington, there's a NOVA program about this last servicing mission to Hubble. So if I say anything wrong today, you can find the corrected information tonight. So, okay. This is 2009 is the International Year of Astronomy, marking the 400th anniversary of Galileo's first observations of the sky with a telescope. It's important to understand Galileo did not invent the telescope. It came from Holland. He was not even the first person to look at objects in the sky with the telescope. The difference between him and all those other guys, though, is that he was a physicist, he was a scientist, he drew inferences from what he was seeing in the sky, he wrote them down, documented what he saw, he brought other people in to look through his telescope to share the information. So it's because of Galileo that the world has a knowledge of this dramatic change in the view of the sky that was brought about by looking through a telescope. And so we honor him in this 400th anniversary year. So let me just give you a little illustration of why Hubble works as well as it does and is so important in science. So what I have here is just years of observations going back to Galileo and the sensitivity improvement over your eyeball. Okay, so, and notice that these are powers of 10. So very, very large numbers. And so here was Galileo, and he gave you roughly a factor of maybe 20 times better than your eyeball here. Then other people came along afterward. Huygens invented better eyepieces and gained a little more sensitivity for looking through a telescope. Shorts created a 21.5-inch telescope, large light gathering capability in the 1700s. Herschel created a 40-inch telescope around 1800. Ross's 72-inch telescope around 1850. You see the idea here is that the telescopes are growing bigger and bigger, able to gather more and more light. The famous Mount Wilson 100-inch telescope, just north of Los Angeles, was where Edwin Hubble actually did his pioneering research that showed that our galaxy, our Milky Way galaxy, is not the only galaxy in the universe, and the fact that the universe itself is expanding, so that the farther away a galaxy appears, the faster it appears to be moving away from us. And of course, telescope sizes continue to grow. Here's the Mount Palomar 200-inch, and you see all along you get orders of magnitude, factors of 10 improvement in sensitivity here. The Soviet Union created a 6-meter telescope, which gave a little improvement in sensitivity here. It doesn't have much of a reputation, so I don't think it worked terribly well, but it was the world record holder at that time. On top of the telescopes, one adds the ability to detect light, first with the naked eye, and then with photographic plates. And so if you can take a time exposure through a telescope, you gain even more factors of 10 in sensitivity. And in the modern age, we have electronic detectors, most notably the charge coupled devices like you have in your video cameras at home or other electronic devices consumers can buy. Astronomers purchase very high quality versions of those to put behind telescopes to really gain dramatic improvements in sensitivity here. Okay, and then along comes Hubble. Hubble is about the same size as this 100-inch telescope on Mount Wilson. What makes Hubble special is that it's above the Earth's atmosphere. The Earth's atmosphere causes starlight to shimmer, and it spreads the light out over a very large area so that a particular spot within the point spread function of a star is fainter than it would be if it was sharply focused. So the main problem with the Earth's atmosphere is that it defocuses images. And on top of that, of course, the atmosphere absorbs light. In particular, it absorbs light in ultraviolet colors. Thankfully it does, because otherwise we'd all have skin cancer and we wouldn't be here. So the atmosphere filters out the ultraviolet light from celestial objects, even like the sun. But that ultraviolet light contains a wealth of information about what objects in the sky are made of and how hot they are. So astronomers really would like to get a look at the universe in ultraviolet light. Similarly, in infrared light, light that is just beyond the red end of the rainbow of colors, red, orange, yellow, green, blue, indigo, violet, right? That's what water droplets do in clouds. They break up sunlight into those component colors, and those are the colors we can see with our eye. So if you go just beyond red, you're into what's called infrared, and at some point that becomes, you detect that because it feels warm. You detect it as warmth on your skin rather than a light that you can see. Again, the atmosphere filters out an awful lot of this, which filters out an awful lot of astronomical information. Hubble is above the Earth's atmosphere, so it can observe across this broad wavelength band, the broad band of colors, and the light doesn't shimmer. It's very, very tightly focused light. And so even a moderate-sized telescope like a 100-inch telescope, Hubble's about 94 inches in diameter, can gain from the fact that the light is strongly concentrated into a tiny, well-focused point. And that's what gives Hubble its sensitivity and the clarity of its vision. Now, this is kind of a busy chart. I threw this in at the last minute because it's a little bit of fun, I think. Our last servicing mission was indeed the last servicing mission intended, shuttle-based servicing mission intended to go to the Hubble Space Telescope. It was the 5th mission. It's called SM4 because NASA has this funny numbering scheme that I'm not going to take the time to belabor, but it was the 5th servicing mission, and I served on all 5 missions, and so that's the reason I just retired. This was the last one. I wanted to go out while I was still batting over 300. But it was, what a long, strange trip it's been. And some of you may know this history, but let me recount it briefly. Actually, originally, this mission was to fly in 2002 and on the shuttle, but for a variety of reasons, mostly having to do with the availability of the shuttle itself, with the construction of the space station going on and so forth, it got shifted to 2004. And then, of course, we know that the Columbia tragedy happened in January of 2004, and that set us back a lot. The servicing mission was canceled. From 2004 March to 2005 March, we were authorized to pursue a robotic mission. Send a robot up. Don't send people up because it's too dangerous, as in the view of the NASA administrator, Sean O'Keefe. But he did allow us to look at how we would send a robot up to repair Hubble, and we actually made a lot of good progress on that score, and we learned a lot about how you might use robots in space. So this was definitely a very valuable exercise. But at the end of the day, it was decided because of a recommendation from the National Academy of Sciences, because of a recommendation from our independent review team, which, by the way, was chaired by Michael Griffin, who later became the administrator at NASA. It was decided that the robotic approach was, just had too many unknowns, and there were too many technical risks associated with it being able to be successful. So ultimately, the robotic mission was canceled. I said STIS fails here. STIS is one of our scientific instruments, and one of the themes of my talk here will be, these are the things that we use to measure light from objects in the sky. And we went through a period, because of the long hiatus of Hubble, of downtime without servicing, when one instrument after another started to fail. And so the basic tools astronomers needed to observe the sky were going away, and the number of tools available in the toolbox was getting smaller and smaller. So in August of 2004, a very important Space Telescope imaging spectrograph failed. Now, after a very serious look at the safety of the shuttle flying to Hubble, it was determined that it was no more risky to fly to Hubble than it was to fly a space station mission. And so the administrator, Mike Griffin, re-enabled the shuttle servicing mission, or reinstated it, in October of 2006. We had another important instrument fail in 2007. This instrument had actually been put on board Hubble only in 2002, so it was only 5 years old when it failed. We were supposed to then launch the servicing mission in October of 2008, but 3 weeks before the launch date, actually, we had an onboard computer that failed. It actually had two redundant sides. Only one side failed, so we were still able to operate. But we decided we really didn't want to send 7 astronauts up and incur all this cost and all this time and trouble, and then go away after the servicing mission and have the other side of this computer fail, and then the mission is over. So it was determined we needed to put in a replacement, properly redundant, properly working computer. And so that caused the mission to be delayed from September of 2008, or October of 2008 rather, to May of 2009. And then you see on May 11th at 2 in the afternoon Eastern Time, STS-125, that's Shuttle Atlantis, was launched with our repair mission. And after the mission was over, Hubble was redeployed back out into space on May 19th. The shuttle landed at Edwards Air Force Base, Dryden Flight Center, on May 24th. And then on September 9th, we put out some of the earliest observations that had been taken with the new instruments and the repaired instruments. So it's been a long road. What a long and strange trip it's been. But fantastically, I'm happy to be able to report that we not only pull the mission off, but that it was fully successful. Okay, just very quickly, and don't worry about acronyms, I'll tell you what this is. This is just to give you an idea of the content of the mission. We had 2 brand new high-technology scientific instruments, a new camera called Wide Field Camera 3, and a new spectrograph called Cosmic Origin Spectrograph. A spectrograph doesn't take pretty pictures, but it's the love of my life. It's the basic tool for astrophysics. It basically takes the light from a star or other object in the sky, and like that water droplet in a rain cloud, spreads the light out into its component colors. And then you can just look at how the colors vary in strength, in intensity, how the brightness of the light changes from color to color. And by doing that, you can tell what the chemical composition of something is, how hot it is, how fast it's moving, how fast it's rotating. So all these basic quantitative physical pieces of information that you need to really understand how objects like stars work. And so that's what a spectrograph does. And so our toolkit needs cameras to take pictures, and it needs spectrographs to do this kind of detailed quantitative analysis of starlight. And it's like, if you don't have a complete set of tools for the astronomer to use, it's like building a house when your toolbox only has hammers. And it doesn't have saws, and it doesn't have drills, and it doesn't have planes, it just has hammers. So now how do you build the house? You don't. The point is that you have to have a complete set of tools. And the main objective of this mission was to restore the full set of tools to Hubble. Because of that, we had these 2 instruments that had failed, an advanced camera for surveys and the Space Telescope Imaging Spectrograph, 2004 and then 2007 here. For the very first time, we asked astronauts in spacesuits to actually take off the side panels of instruments and go in and change out circuit boards. just like you would open up your PC and pull out a circuit board and replace it with one that worked properly. And understand, these guys they're in the weightlessness and vacuum of space. They've got these big balloon-type gloves on and so forth. How do they do that? And I'll show you in a little bit how they do it. The short answer is that we created a large number of tools, very specialized tools for each and every step that they had to take so that they could manipulate the tools rather than have to manipulate the object itself. This is that replacement computer I mentioned that delayed the launch. In addition, we have to keep the spacecraft itself operating, so it needs gyroscopes to help it point. It needs a fine guidance sensor also to help it point at the right position in the sky and to stay very stable so that the images don't get blurred out. We had 6 batteries on board that were the original issue batteries. And so they've been up there for 19 years, and we decided it was time to change the batteries. So we put in 6 new batteries. These are called new outer blanket layers, and that's just some outside insulation to put on parts of the spacecraft that were getting worn to keep the inside of the spacecraft cool. So it just didn't get too hot like this room is. And then finally, there's something called a soft capture mechanism, which I say we, the team, but especially the astronauts, attached to the back end of Hubble so that someday in the future it could be captured, say, by a robotic spacecraft and safely deorbited into the Pacific Ocean so that when it does re-enter the Earth's atmosphere, it doesn't fall on somebody and somebody get hurt. So we have to be able to safely deorbit it probably around 2025 or so. Jennifer read this, and this is something that I kept telling people before the mission. This was the overarching goal of the mission from my perspective as the project scientist. When the astronauts leave Hubble for the last time, it will be at the apex of its capabilities, better than it has ever been before. And this goes back to the theme of restoring all the tools in the toolbox. Not only are we going to put a new camera in, very high tech, we're going to repair a wonderful camera that was already on board but had broken. We have an older infrared camera that is still on board, and it needed to be brought back up to operation. It was down at this time. And that combination of cameras just gave you a full tool set for imaging the universe. Similarly, spectrographs that I mentioned, a brand new high-tech spectrograph, the cosmic origin spectrograph, and a repaired spectrograph. So now, which are very complementary to each other. They don't really duplicate each other all that much. And so those two together give you a full set of tools to do quantitative astrophysics. And then that allows astronomers to continue to pursue the overarching goals of the Hubble mission for as long as it's been up. What is the large-scale architecture of the universe? How is matter distributed in the universe? Turns out it's distributed in a web-like fashion. It's not uniformly distributed like this. And so we want to understand how that web is structured and what role it plays in the origin of galaxies, such as our own Milky Way. Then we want to trace the life story of galaxies from the very beginning of the universe, shortly after the Big Bang, up to the present time. How did our own Milky Way get here? Within galaxies, we work very hard on the topics of the birth and death of stars. And this is a cycle. This goes on all the time. Stars are being born now. They are using up their nuclear fuel and essentially dying a nuclear, because of lack of fuel, they're dying a death. And when they die, they explode or in some way eject material back out into the interstellar medium where new generations of stars can be born. So there's this cycle of enrichment of the material that was produced in nuclear reactions inside stars that through the death process of stars gets put back out as raw material for the next generation of stars. And this is why and I'll mention this a little more later, this is why you and I can honestly say we're made of stardust. Then, of course, round stars, we are discovering more and more planets. They're very difficult to detect, but there are about 300 exoplanets, planets outside the solar system known today. But how do these come into being, and how can you tell whether there might be an Earth-like planet around another star? So Hubble has just begun to break the soil, to put a spade in the soil and start digging into this area with some very interesting results. And then finally, the great themes. 95% of the matter and energy in the universe is stuff we don't understand. We're only about 4 or 5% of what's in the universe. There's dark matter, which makes up about 20 some odd percent. And there's dark energy, which makes up about 75% or so of the mass energy budget of the universe. And we don't really understand any of this stuff at all. But the important thing is to continue to observe, to get clues, and help the theoretical physicists try to probe what it is, what are the strange things in the universe that are so poorly understood. Okay, Finally, that day in May came, and our crew, having waited so long and trained so hard, you can tell they were really happy to be getting out and getting on board. This is Scooter Altman, who's the mission commander. He was also the stunt pilot for Tom Cruise in Top Gun. So all of those wonderful plane shots you saw, you thought Tom Cruise was flying those planes? No, it was Scooter. This is Ray J. Greg Johnson, who was the pilot on his first flight. This is Megan MacArthur, who was the flight engineer and also the person who operated the remote arm that you'll see many shots of in a little bit. She was the only woman on the crew who had to put up with these 6 guys and keep them in line. Drew Feustel, Purdue graduate, therefore twice as capable as any of the others, was one of the spacewalking astronauts. Mike Massimino in the back here is another spacewalking astronaut. John Grunsfeld is the lead spacewalking astronaut on his 3rd flight to Hubble. And this is Mike Good in the back here, who is also a spacewalker. So the spacewalkers go out in teams of 2 every other day. So John Grunsfeld and Drew Feustel were a team. Mike Good and Mike Massimino were a team. You might notice there's a little communications issue there. You have Mike, and they're both in spacesuits, okay? If you want to say, hey, Mike, do this or do that, which Mike? Okay. The trick is they got nicknames. Mike Good was named Bueno, Bueno for good, okay? And Mike Massimino was named Mass, which of course is obvious from his last name, but he's also a big, massive guy. So this was Bueno and Mass. They were a team. Okay, let's see if you can hear this. Approaching the end of the shuttle era. So this will be the last time we'll watch a shuttle launch for a Hubble mission, and that's both exciting and it makes you wistful, a little nostalgic. Can you hear this?
Hubble has arguably been the most spectacular scientific instrument in history, in my opinion. This is the mission that is going to make Hubble actually with the best complement of instruments it has ever had, and prolong its life by installing new batteries, new gyroscopes, and so on.
Hubble right now, before this mission, was sort of hobbling along. It's been 7 years since we serviced it, and you take your 5,000-mile service interval for a car and you say, I'm going to wait until 10,000 miles, things start to break. And we've had that problem, particularly with our scientific instruments. So we're not only going to restore or replenish the toolkit of scientific instruments that we have, but the ones that we're putting in are better than any we've ever had before. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
And liftoff of Space Shuttle Atlantis. Final visit to enhance the vision of Hubble into the deepest grandeur of our universe.
That's Ed Weiler, the associate administrator. It's just preparation, just prologue for what's going to come after this mission is over. With the new tools we have and the incredible new technology we're going to apply to our science, I think the prior years of Hubble kind of opened doors, and now we're going to go through them.
Atlantis is continuing in its due easterly course to catch up with the Hubble Space Telescope one last time.
Little advertisement for Time magazine. I did not get paid for that. So, okay, so I was at Johnson Space Center during the mission. We had many colleagues here, engineers, scientists, and managers to work with the shuttle folks as the mission went along. There were also a very large number of people back up at the Goddard Space Flight Center who operate Hubble itself, because on a mission like this, Hubble is still a working spacecraft. People still have to pay attention to what's going on inside the spacecraft itself, as well, and then coordinate that, choreograph that with the people who are operating the space shuttle. So it's a very complicated operation. This happens to be the day when the crew rendezvoused with Hubble. It's the first time people had seen Hubble for close up since 2002. And so here we are. grasping Hubble with the remote arm, the Canadian RMS system on the shuttle. This is being operated by Megan MacArthur, and although both of these spacecraft are going around the Earth in orbit at 17,500 miles per hour, their velocity relative to each other is effectively zero. It's been nulled out by Scott Altman, who's operating the shuttle, and he zeroes out the difference so that, in fact, it's like the two are at rest relative to each other, and it makes it relatively easy for Megan to grasp a grappling fixture here and hang on to the telescope. And then she will bring it down to go onto this platform, which is, you can barely see her, it's in the back. It's like a lazy Susan. It's a horizontal circular platform that can rotate and tip and tilt. So once Hubble is on that, you can move Hubble around to allow the astronauts to get to various places, various work sites on the telescope. And so here it is now down on this flight support structure. And you can see the remote arm has been pulled away. Okay, just a few shots of the crew in orbit. There's Scott, there's Mass, and Megan. They're preparing a meal here. Ray J, the pilot, John Grunsfeld getting ready to go out, and another shot of Ray J. And they were happy campers in orbit. They really loved to be there. Okay, this is the first spacewalk. We had 5 spacewalks. As I said, 2 astronauts go out in each of the spacewalks. So one crew goes out for 3 spacewalks, another crew goes out for 2 spacewalks, but that second crew is held in reserve. Their third spacewalk is held in reserve for emergency purposes at the end of the mission, if they should happen to need to go out again. So this is John Grunsfeld, and the picture's been taken. You can see the reflection here of Drew Feustel in his visor. I wanted to show you this in particular because you'll notice this and this. Those are helmet cameras, and you see the lights that light up the work site here. And those video stream the images as seen by the astronauts. They're at their work site, and you get a very close-up view of what they're doing at any given time. And so it's really remarkable to be able to watch them work that close up. It's important, too, because in some cases we don't have good shots of the activity they were doing, and so I've inserted a few of the helmet cam shots in here. They're a little lesser in quality, but they at least show what was going on. Okay. 2 new scientific instruments and 2 instrument repairs. From the standpoint of science, that's the part of the mission that I was most concerned about. And the most important task in terms of mission success, the highest priority scientific task, was to replace the old workhorse Wide Field Planetary Camera 2, which was put in Hubble in 1993, still working, but just a very low-tech camera. Take it out and put in this wonderful brand new high-tech Wide Field Camera 3. And so that was the first task on the first day. And we were all excited and pumped and ready to go. Okay, now to get the new camera in, you have to take the old camera out. And it's held in by a single bolt that's actually 55 inches long and it attaches to a latch deep inside the spacecraft. And so you basically just have to apply some torque and unscrew this bolt and pull it out, and then the camera will come out. So we're sitting in the control center that I showed you earlier, and with our headsets on and listening intently to the astronauts, and they tried. And this is a power drill with a sort of a drill bit in it, but it's not a drill bit, rather a screwdriver socket wrench type device in it, and you can set the torque settings to apply just enough torque to twist the bolt without breaking it. So 37 foot-pounds was the torque setting, and they tried it, and it stalled. Nope, doesn't work. Okay, well, let's go up to 40-some-odd foot-pounds. Nope, doesn't work. Let's go up to upper 40s, 48, 49 foot-pounds. Nope, doesn't work. And at that point, you had one panicky project scientist. And so I was on one floor in the control center. I unplugged my headset and went dashing upstairs where all the engineers were sitting, because they had much better situational awareness up there of the intricate details of what was going on. And when I arrived up there, the first thing I heard one of them say was, "Well, maybe it'll just have to break." And and I mean, we don't have any alternatives. Let's just torque it, and if it breaks, it breaks. And of course, if it broke, then the old camera stays in, and the new camera, which cost a bundle of money, comes back to the Earth unused. And the mission is by definition a failure right there on the first day, because that was the highest priority instrument task like that. So what happened? My wonderful colleague from Purdue University, Drew Feustel, his hobby is an auto mechanic. At any given moment, he has 5 cars in his 3-car garage. And his father explained to me how he does that. It's not simple. But he'll refurbish a car, he'll drive it for a couple of years, then he'll sell it and buy some other junker and bring it in and refurbish it. And that's his hobby. He loves that. So he set aside the power tool, took a regular old-fashioned socket wrench, you know, how you might undo lug nuts on your tire, puts the socket head over it's a hex bolt, put the socket head over the hex head, socket wrench over the hex head. He has to push in with a little force because there's a little spring clip inside that has to be sprung apart because it's grasping the bolt. So he does that. And then he applies human muscle power, right? And he does it carefully. He's worried about breaking it, but
Woohoo, it's moving out. 4. Great job, great news.
it was tougher to do than we thought, but you know, it has ended with just beautifully. Well, I've just lost 5 years of my life, I think. So I didn't know their cameras were rolling when I was in there, but I think it does capture a sense of how important this was to all of us, and I could just see the whole mission crumbling down around my head in the first few hours of the first day. But thankfully, it had a happy outcome. And so this is the bay, which is now empty, where the old camera was situated. And now you see the new cameras in place. This white sheet is a radiator that sticks outside of the spacecraft to help keep the camera cool. This is the old camera that's being carried away to be stowed, to be brought back to the ground. Later that day, they also inserted the replacement computer that I mentioned, that had the failure of which had delayed the mission. That went very well, and so here's John Grunsfeld doing that. Next day, it was time for Mass and Bueno to go outside, and their first job was to replace the gyroscopes on the telescope. And so there were 3 boxes called remote sensing units. Here's one of them. Each of them contained 2 gyros. And so it's not simple. This is Bueno on the arm. He's fastened down. His feet are fastened down to the tip of the arm, so Megan MacArthur can just move him around wherever he wants to go. And you see this extra leg sticking out here. That's Mike Massimino. He's in front, and they're heading toward this open payload bay area where the new gyros have to be installed. And you see these devices. These are called fixed head star trackers, and they're pretty delicate, big cameras that actually help navigate the spacecraft. And the remote sensing units are all behind and above these, so you have to get in here and up and above to do that. And so here's Mike Massimino inside, under a fixed head star tracker, being really, really careful not to bump it, putting in one of the 3 remote sensing units. Now, he's the biggest crew member, and you ask, well, why don't you put the smallest crew member in there? Because the quarters are so tight. He had the longest reach, and he was the only one who could actually reach up high enough to get the job done. Okay, next, the third EVA day, the third spacewalk day, the first task was to put in this high-tech new cosmic origin spectrograph, the most sensitive ultraviolet spectrograph ever flown in space. And to do that, the crew had to remove this device called CoStar. This was put in, this was the corrective, one of the 2 corrective set of eyeglasses that was put in 1993 to correct Hubble's blurry vision. You may remember in 1990 when Hubble first flew, we couldn't focus it, and it had a common optical problem called spherical aberration. Should have been caught on the ground and was not. So the large 94-inch primary mirror of Hubble was ground a little bit too flat, about 1/50th the width of a human hair, so just a tiny bit, but that was plenty enough of an error to give it spherical aberration, so it couldn't be focused. So one of 2 devices that were taken up to correct the problem was called CoStar, Corrective Optic Space Telescope Axial Replacement. It had to be taken out to make room for the new cosmic origin spectrograph. And now each new instrument we put in has its own optical correction built into it. So you no longer need an external device like this. This, by the way, is now at the Air and Space Museum being prepared for public display. And so here they take out CoStar, and they put in the new spectrograph. It's a little hard to see here. So here's one of these helmet camera shots. This is John Grunsfeld's helmet cam, and you can see the bare outline. It's about the size of a refrigerator here. It's a rectangular box, and these are the handles that the crew hold onto as they slide it into rails and fasten it into the telescope. Okay, Now, this advanced camera for surveys repair was later that day with Drew Feustel and John Grunsfeld. John Grunsfeld was the prime person for this job. This was the first attempt to actually repair a broken instrument in space, go internally into it and replace circuit boards. This was expected to be by far the most difficult task. It originally was planned to be spread out over 2 days, but John Grunsfeld worked really hard to get the time down so it could be done in 1 day. And it involved a very awkward reach where he had to reach up around the side of the instrument to a diagonal panel, use wire cutters or a special wire cutter to take off a metal grid to get to a panel that was fastened down with 36 screws, and get those screws out to get the panel off and then replace the boards. And oh, by the way, there was a strut in the spacecraft right here, which made it very difficult to reach and to see. Okay. So here they are going to the work site. I love this picture of the Earth. I'll just throw it in. And okay, I mentioned those 36 screws he had to unfasten. They were not captivated screws. So if one got loose, it could just float away. It could float inside the telescope. It could float out somewhere where it would pose a damage hazard to the space shuttle itself. So engineers at Goddard got very creative and produced a wonderful toy called the fastener capture plate here. And you can think of it as just a sheet of plastic with an adhesive surface around the outer periphery. And that sheet of plastic has 36 holes drilled in it in precise locations so that each hole will line up exactly over the head of one of the screws. And then you put a drill bit on a power tool, except a screwdriver bit on a power tool, through each hole. And that lines up exactly and with the head, they're Phillips heads, and you can unfasten each screw that way. But then the screws are sandwiched between this outer plastic sheet, which is fastened down with the adhesive, to the side panel of the instrument. So that when you get all 36 out, they can't float away because they're trapped in that sandwich, and you pull the whole thing out and you stow it, and then you have an available work site. When they did this, the lighting was such as they were moving it around that you could see the screws floating around inside this, and they looked like 36 angry bees. It just looked like a beehive, things floating around. So here's John Grunsfeld. He's already snapped off the wire with wire cutters. He's already snapped off that metal grid, and now he's pre-loosening each of those 36 screws so that they'll unscrew easily when he gets the fastener capture plate on. And so he did that job. It went well, and he pulled out, this is one of 4 circuit boards that he pulled out and replaced with 4 brand new circuit boards plus a new power supply that was attached to the outside of the instrument. And when we tested this instrument shortly after he finished it, it worked great. So the first successful human repair job, you call your TV repairman to go into space and repair a camera. Okay, the next day, this was EVA Day 4, Spacewalk 4. This was the worst day on the mission. Similar repair, except for this was the Space Telescope Imaging Spectrograph. And here there were 111 screws that had to be removed. So we had a fastener capture plate that was that much larger. And this job was to be done primarily by Mike Massimino, supported by Mike Bueno. And so here they're getting ready to go. I want to show you this picture, and then I'm going to back up a second. This is the fastener capture plate already fastened to the side of the instrument, the Space Telescope Imaging Spectrograph. And you see this bracket, and there's another bracket down here. It held on a handle originally, sort of like the handle on your refrigerator door. And the idea was to unfasten 2 screws up here and 2 screws down here, and then the whole thing would come off. Or at least the handle would come off. It would leave the brackets, but the handle would come loose and come out. And that way you made room to get the fastener capture plate inserted properly. Well, Mike unfastened these 2 screws and 1 screw down here, but human error reared its head, and as I would do, he came in on the 4th screw at a little bit of an angle, and he didn't have the drill bit properly seated in the screw head, and so when he turned the drill bit, it reamed out the head. So the screw was stuck in there. And we were already like an hour and a half behind. These EVAs have to last 6.5 hours, and they don't like it a lot if you go beyond 6.5 hours. And we were already an hour and a half behind in that timeline. So we tried some other screwdriver bits. They didn't work. We thought about drilling it out, but the drill bit we had was too small, and it would kick up an awful lot of debris that we didn't want floating around. And finally, some bright guy said, "Why don't we just break it off?" And the concept of purposely breaking something in space is just anathema. You don't do things like that, right? So hastily, some engineers back at Goddard ran a test with a ground version of this, and they determined that if Mike could apply 60 pounds of force at the loosened end of the handle, that bolt should break down here. And had a lot of discussion. The crew needed to be comfortable. They were the primary deciders. Scott Altman, as the commander, had the primary decision up in orbit. And they decided, they were comfortable. They would be willing to go ahead and try this. In discussing this back and forth between the ground and the orbiter, though, we kept using the term latent energy or something like that. Stored energy was what it was. And stored energy is simply the energy that's released if you break something, okay? But it sounded kind of ominous. And so Massimino, before he started, there was a little pause, and he said, could we talk a little more about the stored energy thing? What is that? What exactly is that? Because he was concerned about breaking his helmet, visor, or puncturing his suit, obviously. So here's how it worked out.
That darn handrail. Sunset in 11 minutes.
Houston, you ready for this? Yeah, we're ready.
Okay, man, you have a go.
Here we go. Stop. Disposal bag, please. Okay.
Love it. After all that trauma, he's just matter-of-factly says, disposal bag, please. So now here he does have the fastener capture plate properly applied. Oh, I didn't mean to do that. Let's see. Now I'm going to have to come back. There we go. He's got it properly applied, and let's see if I go. Yeah. And now that 111 screws have been removed, and the plate has been taken off, and here you see him removing the one circuit board. It was only one circuit board that had to be replaced. And here's the tool that was attached to the edge of the circuit board so that the sharp edges of the circuit board could not puncture his spacesuit. I should comment that before he did this, when he finally got the fastener capture plate on, and he took his little mini power tool, little power screwdriver, to start removing the 111 screws, the battery was dead in it. And after all, after the handle breaking and all that stuff, that was just too much. And his words were, "Oh, for Pete's sake." But I suspect his thoughts were a little stronger than that. And so at that point, he went back into the airlock, where we had a spare power tool with a properly charged battery in it. And he stayed in there for a little while. He replenished his oxygen supply. He recharged his own spacesuit battery. So you can do some replenishment like that to extend the length of a spacewalk. And then he just sort of collected his thoughts. I think he was having a Zen moment in there or something. But when he came back out, he was a tiger. And he got the 111 screws unfastened in about 20 minutes. So think of a NASCAR thing. So that went splendidly, and on the ground we were quite happy. I want to point out this guy. This is Preston Birch, who is our lead program manager. This is Frank Sepulina, who is the brain trust for servicing robotic spacecraft in space. He invented and perfected the art and science of how you do that. So all of our servicing missions are absolutely, totally thanks to Frank Sepulina here. Okay, last EVA, we replaced batteries, as you see here. We needed that new fine guidance sensor, so that the old one was taken out, and here's the new one going in. Very complicated optical device that helps keep Hubble very, very stable. And there was even time left on the last day, thankfully, to put on all of our new insulation blankets on the outside so that spacecraft instrument or electronics bays would stay properly cooled. I love this picture. That's the Earth in the background, and you see how many tools they have. There's a tool caddy. He's like 2 6-guns pointing in opposite directions or something. And then Hubble was deployed on flight day 9. And I don't know why I keep getting that, but let me come down here. There we go. And here it's going away from the shuttle. You can see the soft capture mechanism that was attached to the rear end so that someday a robotic spacecraft can grab Hubble to properly dispose of it into the ocean. And yeah, I went from agony to ecstasy, the happiest days to a Hubble hugger, and that was me. And I just have to give credit. I mean, a huge team of people. These were the folks, some of the folks at JSC working Johnson Space Center in Houston, Texas, with whom I worked down there. These are the folks at Goddard Space Flight Center who operated Hubble and choreographed and coordinated the Hubble and the Shuttle Atlantis operations. Here's Senator Mikulski here and here, who came out on the day Hubble was deployed so that she could witness the deployment after the mission was successfully completed. Just a few more shots of the deployment process here. I'm going to come back to that picture on the left in a bit. And of course, after a 3-day weather delay, they had to land at Edwards Air Force Base, and then they had to be towed or carried back to Kennedy Space Center on the 747. And here is the happy crew after they've landed. And of course, we had serious media attention because of the mission. You see, Mr. Magoo now has eyeglasses, and Hubble has very, very sharp vision, and it's the real Star Trek. So we're always thrilled that the public rides along with us on these missions and following Hubble in general, as they paid for the telescope and they deserve to get all the benefit out of it. Now, time is a little short, so I'm going to go quickly. We did release in September some of the early observations taken with the new instruments and the repaired instruments. All 4 of these pictures were taken with the new Wide Field Camera 3 that we almost did not get in. I'm going to pick out just a couple of examples here and tell you a little bit more about them. This is the constellation Carina. It means the ship's hull in the southern hemisphere, and there's a large cloud of gas and dust called the Carina Nebula, and this is a place where new stars are being born all the time. And so this is a ground-based image that's the reason it gets blurry there. But now here's the Hubble shot of this pillar. You may be familiar with the so-called pillars of creation that Hubble took a picture of back in the 1990s. Now look what happens. That first shot, I'll go back, but that first shot you saw was all the dust illuminated by bright stars all around, bright hot stars, and that was seen in visible and ultraviolet light. But now this new camera also has an infrared light capability, and when you look at the same object with the infrared capability, you can see through the dust, and you can see this new star being born and ejecting these jets, taking energy away from the star and allowing it to slow down in its rotation. So here's the pillar again, a little close up, and notice these things. We could see evidence of the jets, the 2 jets coming out at opposite directions from each other from the new star being born, but we didn't know for sure what that was until we looked in the infrared. And now you see the new star being born and the jets being emanated from it. So this idea of a very wide wavelength coverage is just remarkable, because things look very different in one color than in another color, and you can get a broad suite of facts and information about particular objects just by looking at them in different colors. And our new camera enables that. Now, that star's being born. Here's the same camera looking at a star in the process of dying. This is the way our sun will die at about 5-6 billion years from now, if you're worried. And so what's happened is the star has burned up all its nuclear fuel. It's a fairly low mass star, so it doesn't explode as a supernova, but it just sort of gives off gasps of its outer layers of material, which have been enriched by the nuclear processes, the nuclear reactions going on that powered the star during its lifetime. So the primary source of carbon in our organic chemistry, for example, is exactly this. It comes from exactly this process. Hydrogen is converted to helium, which is converted to carbon, and the star goes through a phase where it can't get hot enough, squeeze tightly enough to get high enough pressure in its interior to get the temperatures up to ignite new nuclear reactions. So it goes unstable, throws its stuff out. It's enriched in the carbon that was produced in the nuclear reactions. And you do get a little carbon from other types of exploding stars, supernovae, but this is the primary source of the carbon in our bodies. And you are made of star stuff. Now here's a more massive star that's maybe 20 times the mass of the sun, 30 times the mass of the sun. It ends its life explosively, goes unstable and explodes, and again ejects this material out into what we call the interstellar medium, where it provides the nuclear processed heavy elements to make new generations of stars. That was an artist's concept, of course. Here is a real supernova remnant, and we focused our brand new cosmic origin spectrograph on that little cloud, that little remnant cloud from the supernova. And this is what we saw. Now, I said we don't take pretty pictures, but we spread the light out into its colors, right? This is color, and this is brightness. And we see that at some colors, the light is much brighter than at other colors. And those are characteristic, what we call emission lines, that are due to carbon and oxygen that were produced in this exploding star. A little bit of carbon. This is the main source of oxygen in the galaxy. The oxygen we breathe came from exploding stars like this. So this is and this is a very faint object, and the idea of cosmic origin spectrograph is to be able to observe very faint objects. So that's what it does. Let's go back into that same Carina Nebula, the ship's hull, or the ship's keel nebula. Here's a very exotic object. There are two very, very massive stars in orbit around each other. They're very unstable. They're going to blow up sometime in the next 100,000 years. And when they do, people on Earth will see it, and it'll be a very spectacular daytime event, not to mention nighttime event in the sky. Probably immense amounts of energy will be given off, including gamma rays. It's about 7,500 light years from us, and we think that's far enough that we're safe. Okay, but sometime in the next 100,000 years, this is going to be a spectacular light show. What we have today is the ability to observe this before it blows up and look at the processes and phases it's going through in advance of that event. And so the newly repaired Space Telescope Imaging Spectrograph is able to line up a narrow slit along the object itself and spread the light out from each and every point into component colors. And you see the chemical composition: iron, nickel, argon, helium. You see how those lines intensify or get fainter as a function of where they're seen along this line of sight. You can tell what direction things are moving, because some of the lines are shifted toward the blue and are moving toward us, and other lines are shifted, and the other part of the line is shifted toward the red, moving away from us. So lots of physical information that this newly repaired instrument will reveal. Final example, just watch this on the left. Einstein said in his general theory of relativity that mass is capable of distorting space, and light passing through that space bends. And so if you had a black hole in downtown Baltimore, passing along like this, a very massive black hole, that's how the image of the background buildings would be distorted. Okay?
That's the only way they can detect black holes anyways.
No, it's actually...
Since it bends
Let me go to my next slide. Now, we're going to detect something, but it's not the black holes themselves. I just used black holes as an example. It could be any heavily condensed matter. It could be dark matter, for example. Anything really heavy and massive would distort light like that. Now, we have another example called a gravitational lens. Say a distant galaxy, light coming from it toward Earth, and now there's an intervening mass, a big, rich cluster of galaxies that is embedded or imbued with a lot of dark matter that you can't see. And that acts as the same kind of lens. And this is a real observation now, and you see these arcs. Those are the distorted images of galaxies that are way off behind that intervening conglomeration of mass. And so here's an example taken with the newly repaired advanced camera for surveys, and you see the distorted images of the background galaxies. And again, for every pound of light matter, for every pound of galaxy light or matter that's in a galaxy, there's 5 pounds of cold dark matter, which we don't understand the nature of. The universe, 20% of the mass energy budget of the universe is cold dark matter. Probably it's made up of some exotic particles left over from the Big Bang origin of the universe, but and the Large Hadron Collider and Fermilabs and other laboratories are, as we speak, hoping and attempting to reproduce or recreate particles of this type on the ground in the laboratory in particle accelerators. But in the meantime, there are just speculations about what dark matter is. What we know about it is that it exerts ordinary gravity. It can cause galaxies to move around. It can bend light, as it does here. And you can also actually use this kind of observation to map the distribution. So there are 2 clumps of dark matter surrounding these 2 very bright elliptical galaxies. And I love this one. We call this the dragon. There are a few examples of the arcs and so forth. See the distortion of that distant galaxy image just produced by the mass of this intervening galaxy. But look at this guy. I'd never seen anything like this before. We call it the dragon. There's the head, there's the tail. It's actually an image. It's actually 4 or 5 lensed images of the same galaxy that's about twice as far away off in the background behind this large cluster of intervening galaxies, which are all held together by their own gravity and by the dark matter's gravity. But has had the effect of actually bending the light, so you see an image of the galaxy there, fairly clear image. It was a spiral galaxy, and an image here. But then this is just 4 or 5 images of the same galaxy stretched out and distorted so much you can't really discern it. See how it arcs over there? That's just distortion of the light produced by that little galaxy there. That's Einstein's general theory of relativity before your very eyes. Okay, I'm going to conclude. I'm a little bit over time. This is the most important shot from the mission, as far as I'm concerned, and I always try to conclude my talks with this. This is after Hubble has been deployed, and the spacecraft is moving tail first in its orbit. So the sun is rising here, and we're looking back at the Earth, and notice the Earth's atmosphere right here. That's it. So that's all that's keeping us alive. And if you worry about things like global warming or air pollution or the ozone hole disappearing or being created, and therefore that skin cancer producing ultraviolet light being able to get to the ground, that's the only thing that's protecting us. And it seems to me the most important thing astronauts learn when they go out into space is to look back at our own Earth and see how fragile it is. And I think this is the kind of evidence that isn't hypothetical or speculative. This is a direct evidence of how hard we need to work to take care of our own planet. And that's all.
Dr. Leckrone will answer a few questions. Do you want me to pick?
Yeah, why don't you pick?
We'll start in the front.
When you're doing attitude control with gyroscopes, do they run continuously? And if so, is wearing out over 7 years a concern?
Yes, that's been the main failure mechanism on Hubble that's given us problems in the past. We have 6 gyroscopes. We only need to use, actually, as originally designed, we needed to use 3 at a time. So we could turn 3 off and have 3 at a time operating. What we found was that there were wear out and breakage mechanisms, and the longer they operated, the more likely they were to fail. And so we created a 2-gyro control law, and actually prior to this mission we were operating with only 2 gyros at a time. We also created a 1-gyro control law, and in principle we could operate with 1 gyro at a time. You still get the same image quality, but there are huge swaths of sky that you're not able to observe at any given moment if you're on 2 or 1. Thankfully, we now have 6 beautifully working new gyros on board, so we're back into our normal 3-gyro mode. But 4, 5, 6 years is a typical gyro lifetime, and that's the reason you need to regularly service Hubble and have backup gyros.
We'll start in the back and then come back. I'll take the back.
Do you know whether Hubble has been pointed at Wolf-Rayet 104 and the possibility of the supernova?
Wolf-Rayet 104.
Correct. It's a binary system, may go supernova in about 200,000 years.
Okay.
And if we're lined up on the bullseye, that little atmosphere is going to disappear.
Yeah, that's similar to the situation with Eta Carinae that I showed you right at the end.
That is a lot closer.
Okay, the answer is no. I specifically don't know, but Hubble's archive is a public archive, and all you have to do is go to stsci.edu, Space Telescope Science Institute, and you get access to the archives, and someone there can help you get access if you're not able to do it easily, and you can look up that target.
Thank you very much.
Yeah.
I'd be interested to know if you're considering writing about either any of your experiences or what you've learned, or have you already? And donate it to the library.
Okay, the answer is I retired 10 days ago. One of the things I really want to do is write a memoir. It's hard. First of all, I never kept a diary, which is a bad mistake. Anybody who's thinking of doing this and you're a young person, keep a diary. I know it's boring, but do it every day. So the question is, how accurate is the old memoir, anymore? But I do want to write a memoir. It's a rich subject. I have written about Hubble before, encyclopedia articles and that sort of thing. But it's such a rich subject, and yet it can be fairly technical. So I want to write something that would be interesting for people to read. So yeah, that's my plan. I sometimes think instead of writing a memoir, I would prefer to write a historical novel, so that the things I forgot I could just make up.
The nature of dark energy seems to be a complete enigma now, and I was wondering what Hubble is doing to address that problem.
Yes, the one thing that Hubble was part of a flotilla of telescopes, including ground-based telescopes, that first identified this dark energy phenomenon back around 1996, 97. It was identified because we have a technique for measuring how far away galaxies are, and it involves a particular kind of exploding star called a Type 1a supernova. And the physics that causes this particular kind of star to explode is very predictable. It's the same phenomenon again and again, just in different galaxies, different cases, different examples. And so what you can tell very predictably is how intrinsically bright these stars get at their maximum output of light. And that then the only thing that's keeping you from knowing how far away they are is the relative brightness compared to other similar stars. The closer they are, the brighter they'll look. The farther away they are, the fainter they'll look. If you can calibrate that relationship, that allows you to calculate the distance to each and every galaxy where you see these stars. And at the same time, you can use a spectrograph to measure how fast the galaxies are moving, predominantly because of the expansion of the universe, how fast they're moving away from us. And so if for a given galaxy, you know how fast it's moving away from us, and you know how far away it is, you know how far back in time you're looking, then you can say at that time the universe is expanding by this particular rate. I've just measured it. And so the trick is to do this over and over and over again, get thousands of examples of these supernovae all around the sky, and get some idea of basically a time history, a chronology of how the expansion of the universe changed over time. The common wisdom when I was in graduate school was eventually the universe will slow down. And the only question is, how long will it take? How slow will it get? And how long will it take to maybe implode, slow down and maybe implode back in on itself? That's because gravity, everything that exerts gravity, including the dark matter in the universe, tugs on everything else. And so the expansion should be tugged and slowed down by the gravity. What was found instead by using this technique I just described is that at the present time, the universe is not slowing down, it's speeding up. It's like I threw a baseball into the air and it never came back down, and I'm looking for it with my ball glove. It is in effect a repulsive gravity. That term has been used to describe it. But in point of fact, no one really has a clue. The only clue comes again from Einstein. Einstein, when he did general relativity, thought the universe had to be stable, not expanding or whatever, or contracting. And to keep it from contracting, falling back in on itself due to its own gravity, you have a stable universe here. It's supposed to be there and not move, not change. How do you keep it from falling back in on itself? He put in an artificial constant in his equations that he called the cosmological constant that exerted a repulsive gravity to keep the universe from collapsing. And then he met Edwin Hubble, and in fact, they became, I don't know about friends, but they did exchange correspondence and that sort of thing. And Hubble said, no, you're wrong. We don't live in a stationary or static universe. The universe is expanding. I've proven that observationally. And so Einstein said the cosmological constant was his worst mistake, and he pulled it back out of the equations. Now we're in a position where we have to find some mechanism for creating a repulsive gravity. So guess what? People have resurrected Einstein's fake fudge constant and are considering whether the dark energy that we're measuring is consistent with being a constant in time and consistent with the value, the number that you would derive from that constant that Einstein put in. It's a very difficult problem. So the long answer. Short answer, the summary answer is the way you work with Hubble is you just keep observing these supernovae as far back out in time and across space as you can, collect a statistically as large a sample as you can, get the error bars down lower and lower. And the two things that we hope to be able to answer is it a constant or does it change with time? and if it the magnitude of the dark energy, and if it changes with time, by how much. And there, we have dedicated space missions that are being designed, one called JDEM, Joint Dark Energy Mission, that whole purpose in life is to go out and measure gazillions of supernovae of this sort and get the statistics really, really good. But I mean, this is a big problem in theoretical physics. This is not just a problem in astronomy or astrophysics, because this has to do with the fundamental tenets of physics as we understand it, including gravity. And so observationally, what we can do is just give as many clues as we can to the theorists to get them maybe going down the right track of thought. But it's a very perplexing problem, the most difficult physics problem on the table today, really.
Do you feel, now that you've been through the whole process, that enough thought was given to designing the Hubble for maintenance?
Hubble was designed from the beginning to be maintained, and it was designed in tandem with the space shuttle, in a sense each scratched the other's back. You know, because we were a shuttle payload, that made us a little more popular in Congress, and because the shuttle had this important payload to point to, that made them a little more popular in Congress. And so we both came to life at about the same time. And because we were related to the shuttle program directly, the idea was to make Hubble serviceable from the very beginning. That isn't a new idea that was invented just after spherical aberration. The issue, of course, was budget. It cost money to design a spacecraft in any particular way, and as budgets got cut, fewer and fewer components were deemed to be serviceable in Hubble. In other words, things that were on the shopping list of things that you could service in Hubble, that shopping list got shorter and shorter and shorter. Like, you could replace batteries, but you couldn't do X, Y, or Z. What we have found is that human beings are incredibly creative, and there's nothing on Hubble we can't fix except the primary optics. That's what we found out. And Frank Ceppeline, I showed you his picture. He's supposed to retire any time, and I don't think he'll retire until he keels over. I mean, because he loves this stuff, and he loves inventing these techniques and these tools. And he's always out advocating, let's do more, let's service other spacecraft in addition to Hubble, or build new spacecraft to be serviceable and that sort of thing. But it was basically a budget driver that limited the list of items that could be easily serviced. But at the end of the day, we figured out how to service things that were never intended to be serviced on Hubble.
Okay. Good. One more?
Yeah.
Oh, now there's three more.
It's okay.
I mean, we could.
I'm good if you're good.
In what way was the new camera more advanced than the old one?
Okay. The old camera did not operate in the infrared. So the old camera operated in the ultraviolet and visible only. And so we extended the wavelength coverage. We actually have two independent camera channels inside that box, and one of the two channels goes all the way out into the infrared. Secondly, the light detectors, the electronic detectors, the charge couple device, which is used for the ultraviolet and visible, and what's called a mercury cadmium telluride, mercad telluride detector that's used for the infrared, are state-of-the-art, absolutely state-of-the-art. And this is a beautiful thing about servicing, by the way, because the infrared detector in particular just came off the assembly line like a year and a half before we flew. And there would be no way with a disposable spacecraft that had been fully integrated and tested, you wouldn't go in there and change anything. But because we were working at the instrument level and not the whole spacecraft level, we easily could go in and substitute the brand new best detector just off the line for the earlier detector we had planned to fly. And it's just amazing. I mean, astronomers are just going crazy with this. And I will tell you that they have already used that infrared part of the new camera to observe farther back in time than anyone's ever gone before. And that's that paper that's already out there. It's being refereed for release, and that will be a news release, I'm sure, within the next month or two.
At what time the fourth repair mission with the substitution of new instruments was to be canceled? It was a decision of the Bush administration. Do you understand the motivations
Yeah, it was a decision by the administrator of NASA, Sean O'Keefe. It came shortly after the Columbia tragedy. Columbia broke up, disintegrated on re-entry, killing 7 astronauts. And that was the second accident of that sort that we had suffered in the shuttle program, including Challenger in 1986. Sean O'Keefe, this is not to disparage him, but he was less technical in his orientation than some other NASA administrators had been. He was largely a business type person. And just as an ordinary person, he felt in his gut he didn't want to go to any more funerals. And he said, okay, we had to finish building the space station, but if something bad happens, the crew, the astronauts, can use the space station as a safe haven, until we can send up another shuttle to bring them down, or use the Soyuz, the Russian Soyuz, to bring them down. Whereas if you go to Hubble and something bad happens, there's nothing you can do, and you're going to lose 7 more astronauts. And people at that time were really challenging the safety of the whole shuttle system. So when Mike Griffin came along, he was more technically oriented, but he was no less worried. And he said, okay, I've heard what Sean says. I know the engineering arguments and the statistics, failure statistics arguments myself. Prove to me you can overcome those obstacles and make a flight to Hubble at least as safe as a flight to the station. And so we spent many, many months. And Mike set the bar very high. And we were able to prove to his satisfaction that we could make the safety of this flight as comparable to the safety of a space station mission. One way to do that was we had a rescue shuttle on the pad ready to go, and it could have been launched within just a few days if the crew went up and discovered terrible tile damage or something like that. So there was a rescue vehicle ready to go, and that's what really made the difference in the statistics. It's still a dangerous game. It's the odds of loss of crew and vehicle are about 1 in 80, and so that's not good. And that's the reason the shuttle is going to be retired and hopefully replaced with another system that has a little better odds built into it. But this crew in particular, they evaluated, there are some things these people would not do in space at the risk of their own lives, but repairing Hubble was something they unanimously wanted to do because they thought the contribution they were making to humankind was worth the risk to their own lives. And so that's the motivation. It was basically a view that the safety was unacceptably low, safety factors were unacceptably low, and then working the system to prove and come up with techniques to improve those safety factors so that it was acceptable.
Okay. I think, okay, fine, so.
Just wanted to know what you're doing in your retirement, and are you going to stay connected to everything going on?
I will stay connected. I'll have an emeritus position at Goddard Space Flight Center, so I'll still be around, and I'm going to do some consulting, and I want to do some writing, like to do a little traveling. But yeah, I'm an astronomer first and foremost, and I'm the world's leading Hubble hugger, and I always will be. And if there ever is an issue or a problem that arises, I'll be there to help if they want me to be there to help. So I'm on call.
This has been a presentation of the Library of Congress. Visit us at loc.gov.